Hello everyone, how are you? Welcome to Edishaw's 50 Days 50 Topics course for UGC NET JRF. Today is Mathematics Day and today I will be discussing the topic of continuity for you people. So we will be continuing from limits. Okay. So we have already discussed the concept of limits. So a function is said to possess a limit at a point x equals to a if and only if its left hand limit is equal to right hand limit, as we have already discussed. So this is the point A. If I approach A from the left, the elements will be of the type A minus H. From the right, the elements will be of the type A plus H. So the left hand limit is of the type limit H tending to 0, f of A minus H, where y equals to fx is the function under consideration. And the right hand limit is a limit h tending to 0, f of a plus h. Now, so we all have done functions like this, like if fx is x square minus 1 upon x minus 1. So we know that f1 is 0 by 0, which is not defined. So this particular function is not defined at 1. But if we talk about the limit of this function at 1, so by common factorization property, this limit will tend to be limit x tending to 1, x minus 1, x plus 1 divided by x minus 1. The common factor will get cancelled. We put x equals to 1, the limit is 2. So we notice that even though the function is not defined at the point x equals to 1, the limit exists. Okay. So what is continuity of a function? So when is a function said to be continuous at a point? So for continuity at x equals to a, the first condition is that fa must be defined. Okay, so we cannot discuss continuity of a function at a point if the function is not defined at that point. But we can talk about limit of a function at a point even though it is not defined at that point. So that is the difference between limit and continuity at a point. So continuity is an extension of limits. Okay, so for continuity at x equals to a, the function must be defined at x equals to a. Second, the limit of the function at a should be equal to the functional value. So this is the definition of continuity. So what should happen? I should be having a graph like this. If this is my point A, so this will be FA. So when I approach A from the left, the function is approaching FA. When I approach A from the right, the function is approaching FA. And also at A, the value FA is existing. Okay. But if we have a graph like this, where we have a hollow circle at A, what does it mean? There is no value of the function at A. Okay. So we can see that it tends to reach FA from the left as well as right. But the functional value at A is not existing. Or it might happen that A, the function takes some other value, say f of something else. So this is not this particular value. F of A is something else. It is not equal to the limit. So in both the cases, the function will not be continuous at A. So what is the definition of continuity? To discuss continuity at a point A, the function must be defined at that particular point. Second, the limit of the function at that point must be equal to the functional value at that. Okay. Now let us discuss some examples. So for example, let us consider a function fx, which is x plus 1 when x is less than or equal to 1, and which is 2x when x is greater than 1. Okay. So now you can see that when x is less than or equal to 1, the function is a linear function. It will be a straight line. It will be continuous. When x is greater than 1, again it is a straight line. It will be continuous. So where will the continuity be doubtful? The continuity will be doubtful at x equals to 1 because the function is changing. Because the function is changing around x equals to 1. So whenever there is a change in pattern of a functional expression around a point, we should be doubtful about the existence or have of continuity of the function at that particular point. So let us check the continuity at x equals to 1. So when we check continuity at x equals to 1, first of all, we will have to check the value of function at 1. The functional value at 1 is now, here is an equal to sign. So functional value will be taken by this expression. So 1 plus 1, which is 2. The left hand limit is limit x tending to 1, the left hand expression. Left hand means less than 1 expression. So this is 1. So this is the left hand. Left hand is x less than 1. Right hand is x greater than 1. So on the left hand, the functional expression is x plus 1. So the limit is 1 plus 1, which is 2. On the right hand side, the expression is 2x plus 1. So this is going to be 2 into 2x. So this is going to be 2 into 1, which is 2. So note that the limit is equal to 2. Okay. And the functional value is also equal to 2. Both are equal and therefore the function is continuous at x equals to 1. So at x equals to 1, we do have continuity of the function. Okay. Now let us take another example. Let us consider fx to be sin x upon x when x is equal to not equal to 0, and let this be 2 if x is equal to 0. Okay. So note that f0 is equal to 2. Okay. Now what is happening at 0? This is taking the value 2. If it is not 0, the value is determined by sin x upon x. So therefore, the point at which the function is changing expression is x equals to 0. So we should be discussing the continuity of the function at x equals to 0. So f0 is equal to 2. And let us talk about limit x tending to 0 fx. So which will be limit x tending to 0 sin x upon x. This is a trigonometric limit and this is equal to 1. So notice that the value of the limit and the functional value are not equal. And therefore, this function will not be continuous at x equals to 0. Okay. Let us take another example. Let fx to be x upon mod x when x is not equals to 0 and 0 when x equals to 0. So discuss the continuity of this function. Again, we will discuss the continuity of the function at x equals to 0. And why would we discuss the continuity of the function at x equals to 0? Because at x equals to 0, the function is changing expressions. Now we will be using the property of absolute value function or definition of absolute value function. So we can see that absolute value of x is minus x if x is negative, and it is x if x is positive. So I can write this as x upon minus x if x is negative, 0 if x is equal to 0, and x upon x if x is positive. So therefore, it is minus 1 when x is negative, 0 when x is equal to 0, 1 when x is greater than 0. Okay. So note that functional value at 0 is 0. The left hand limit is limit x tending to 0 minus 1, which is minus 1. And the right hand limit is limit x tending to 0, 1, which is 1. Note that this particular function does not even have a limit x at x equals to 0. Forget about the continuity of the function. So though the functional value is existing at this particular point, but this function does not have a limit at x equals to 0. And therefore, this particular function will not be continuous at x equals to 0. Okay. So let us take one more example. Let us take fx to be the function mod x minus 1 plus mod x minus 2. So let's try to simplify this function and we need to discuss the continuity. So to discuss the continuity of this function, we should be interested in the points where the function is changing expressions. So you see that when is this absolute value equal to 0? When x is equal to 1. And when is this absolute value equal to 0? When x is equal to 2. So let us plot 1 and 2 on the number line. Okay. So case 1, when x is less than 1. Okay. So fx. Now when x will be less than 1, x minus 1 will become 1 minus x, because when x is less than 1, x minus 1 will be negative, and therefore the absolute value, to remove this absolute value sign, we have to invert this expression. Plus, again x is less than 1, therefore it is less than 2 also. Again we have to invert this. So this is 3 minus x. At x equals to 1, fx will take the value 0 plus mod of minus 1, which is 1. Between 1 and 2, okay, what is going to happen? Between 1 and 2 means x is greater than 1. So this expression becomes x minus 1. X is less than 2. So this expression becomes 2 minus x. So this is 1. Okay. Now at x equals to 2, this expression will become 1, because 2 minus 1 is 1 and 2 minus 2 is 0. And x greater than 2, this expression fx will become, if it is greater than 2, it is greater than 1 also, it will be x minus 1 plus x minus 2, which is 2x minus 3. So if we simplify, our function will be 3 minus x when x is less, 3 minus 2x when x is less than 1, then 1 less than or equal to x less than or equal to 2. This value is 1. Okay. And when x is greater than 2, it is 2x minus 3. So this is my expression for the function. Now notice that this particular function is changing expression at two places. One is x equals to 1 and the other is x equals to 2. So we will check the continuity at x equals to 1 and at x equals to 2. So we check the continuity at x equals to 1. So what is your f1? Your f1 is 1. Your left hand limit at 1 is limit x tending to 1, 3 minus 2x, which is 3 minus 2 times 1, which is 1. And your right hand limit is again 1. So the functional value, the left hand limit and the right hand limit are same. So therefore the function will be continuous at x equals to 1. Now let us check continuity at x equals to 2. So what is the functional value at 2? The functional value at 2 is 1. The left hand limit is also 1, because on the left of 2 we have this value. And the right hand limit at 2 will be limit x tending to 2, 2x minus 3, which is 2 times 2 minus 3, which is 4 minus 3, which is 1. So therefore this function is continuous at x equals to 2 also. So in fact, if you make an observation, the function fx equals to mod x minus a is continuous at x equals to a. Similarly, fx equals to mod x minus a plus mod x minus b is continuous at x equals to a comma b. And this process will go on. No matter how many absolute value functions you add, it will always be continuous at all those points where the absolute value expressions are becoming 0. And at other points, there is no need to worry at all. At other points, it is automatically continuous. So we check the continuity of a function only at the points where it is changing its expression. Okay. So let us do another type of problem. So find the value of k. Find the value of k so that fx equals to 1 minus cos 2x upon x square and x equals to 0, x not equals to 0 is continuous at x equals to 0. So we have to find the value of k so that this particular function is continuous at x equals to 0. Okay. This is the function. Okay. So now for the function to be continuous at x equals to 0, we must have f0 to be equal to limit x tending to 0, 1 minus cos 2x upon x square. Okay. Now what is f0? f0 is given to be k. So k should be equal to limit x tending to 0, 1 minus cos 2x upon x square. Now try to put x equals to 0. So when we put x equals to 0, it will be 1 minus cos 0 divided by 0 square. Cos 0 is 1. So 1 minus 1 divided by 0, which is 0 by 0. So 0 by 0 form is indeterminate form. Therefore, we go for L'Hopital rule. So according to L'Hopital rule, this particular limit will be limit x tending to 0, the derivative of the numerator divided by the derivative of the denominator. Okay. So what is the derivative of the numerator? 0 minus, what is the derivative of cos? Minus sine 2x. And then by chain rule, what is the derivative of 2x? 2. And what is the derivative of x square? 2x. So this 2 and 2 will go away. So this will be limit x tending to 0, sine 2x upon x. Okay. Now we multiply and divide by 2. Now this is the trigonometric limit. This is equal to 1. So therefore, the value of k will be equal to 2 times 1, which is 2. So therefore, the value of k, so that the given function is continuous at x equals to 0, comes out to be 2. Okay. So we have discussed continuity of a function. What is continuity of a function? A function is said to be continuous at a particular point when the left hand limit at that point is equal to the right hand limit at that point is equal to the functional value at that point. If the function is not defined at that particular point, okay, the function cannot be continuous. The function has to be defined at a particular point to discuss the continuity at that point. Okay. Now, after continuity, we come to another thing which is called differentiability of a function at a point. So, differentiability of a function at a point. Differentiability of a function at a point x equals to a. So, what do you mean by differentiability? Now, if you talk about dy by dx, which most of you must have seen in economics, it is very simple. This is called rate of change of y. Rate of change of y with respect to x. This means this is change in y divided by change in x. Okay. So now what is happening? You have a function y equals to fx and there is a point A. Okay. So what is happening? I am going to A from the left and from the right. On the left, any point is of the type A minus h. On the right, any point is of the type A plus h. Okay. So from the left hand side, what is the rate of change? And the functional value at this point is fa. The functional value at this point is fa minus h. And the functional value at this point is fa plus h. So when you go from the left hand derivative. So what is happening? Final value, that is rate change in y. So what is change in y? fa minus h and change in x. What is change in x? A minus h. So which is h. So this is the change on the left hand side. But as we grow close to a, because I'm talking about derivative at a, we have to let h go to 0. So this will be limit h tending to 0. So this is the left hand derivative at a. Similarly, right hand derivative at a is limit h tending to 0. Now, From the right, the final value is fa plus h. The initial value is fa because I am talking with respect to the point, and the change is h. So this is the right hand derivative. So what is the function of differentiability at a point? A function is said to be a function y equals to fx is said to be differentiable at x equals to a if and only if the left hand derivative at a is equal to the right hand derivative at a, and the common value obtained is called f dash of a, or we call it at f dash at x equals to a, or we call it as dy by dx at x equals to a. So what is the definition of derivative at a point? Derivative at a point is nothing but the value of the left hand derivative and the right hand derivative if at all they are equal. This is regarding differentiability of a function at a particular point. Now, suppose you have to check the differentiability of a function. So, for example, if you look at fx, so if your fx is 2x minus 3, x less than 3, and equal to 3, and if it is 2x plus 3, x greater than 3. So again, where is the function changing expression? The function is changing expression at x equals to 3, so we should be worried at x equals to 3. Okay, now for differentiability to occur, the function has to be continuous. So for differentiability at x equals to a, the function must be continuous at x equals to a. We cannot talk about differentiability of a function at a point if it is not continuous at that point. It is of no use. So what is f3? f3 is 2 into 3 minus 3. We will look at this expression because there's an equal to sign here. So which is 3. Okay. What is the left hand limit at 3? So this is limit x tending to 3, the left hand side, which is again 3. And what is the right hand limit at 3? Which is limit x tending to 3. Okay. So 2x plus 3, which is going to be 2 times 3 plus 3, which is 9. So therefore, you can see that the functional value and the left hand limit at 3 are equal, but the right hand limit at 3 is not existing at all. So the function is not continuous at x equals to 3. So therefore, it will not be differentiable also. But where is the student likely to make an error? You see, if you look at the left hand derivative, so you will find the derivative of the left hand side, that is 2x minus 3, which is 2. And if you look at the right hand derivative, you will find out the derivative of the right hand side, which is derivative of 2x plus 3, which is again 2. So you might be tempted to decide or conclude that as the left hand derivative and the right hand derivative are equal, therefore the function will be differentiable at x equals to 3. But you have to take care of the fact that the function is not even continuous at x equals to 3. Therefore, let's not talk about differentiability. So whenever you have to talk about differentiability of a function at a particular point, you have to take care of the fact that it is continuous. So first you have to make sure it is continuous at that point. And after that, you can go on to discuss the differentiability of that function. Okay, let us discuss one more problem. So we will do it the h way, that is the limit h tending to 0 way. So discuss the differentiability of this function. So discuss differentiability at x equals to 1. So let us try to break this function. The function will be, when x will be less than 1, it will be 1 minus x. When x will be equal to 1, it will be 0. And when x will be greater than 1, it will be x minus 1. So first of all, we'll discuss the continuity. So continuity at x equals to 1. So what is f1? 0. What is left hand limit? limit x tending to 1, 1 minus x, which is 1 minus 1, 0. What is right hand limit? Limit x tending to 1, x minus 1, which is 1 minus 1, 0. So the functional value, the left hand limit, the right hand limit, all are equal. Therefore, it is continuous at x equals to 1. That is verified. And now we can go on to discuss the differentiability. So let's try to find the left hand derivative at 1, which should be limit h tending to 0, f1 minus f1 minus h divided by h. And the right hand derivative at 1 will be limit h tending to 0, f1 plus h minus f1 divided by h. Now, f1 minus h. 1 minus h is less than 1. So, therefore, we will be here. So, it will be 1 minus h. So, that should be h. And what is f1 plus h? 1 plus h is greater than 1. So, we should be here. It should be 1 plus h minus 1, which is h. So, this will be limit h tending to 0. f1 is 0. 0 minus h by h, which is limit h tending to 0 minus 1, which is minus 1. And the right hand derivative, limit h tending to 0, f1 plus h is h, f1 is 0 divided by h by h is 1. So the limit is 1. So you can see that the left hand derivative and the right hand derivative are not equal to each other. Therefore, the function is not differentiable. But if you are talking about a multiple choice question, so there is no need to go the h way. Okay. What you can do, you can differentiate this and you can find it as minus 1, and you can differentiate it, you can find it as 1. So the left hand derivative is minus 1, the right hand derivative is 1, they are not existing. Therefore, the function is not differentiable. But please be cautious of the fact that you have to check the continuity of the function at a point before discussing its differentiability at that particular point. So this is all about continuity and differentiability of a function at a point. Not a very difficult concept. This is a topic which has to be understood rather than, questions to be practiced. Because if you understand it, it is not difficult to check the left hand limit, right hand limit, or left hand derivative or right hand derivative. Okay. But if you don't understand it, no matter how many questions you do, if you don't understand the concept clearly, you might end up with the wrong answer. So thank you for joining. Please stay tuned to our channel to have knowledge of such more concepts which are important for UGC NET JRF exam. All the best. See you again.